AP Chemistry fodder. Let's get to the questions here. So here we go. We're going to start with question number 1. It says, answer the following questions about magnesium. An incomplete mass spectrum for magnesium is shown in the diagram, and it says the percent abundance is 79%. So get our little pointer here. The percent abundance of the other two natural isotopes of magnesium, 25 and 26, are approximately equal. Okay. So it says complete the mass spectrum in part A by drawing thick lines in appropriate locations to represent the percent abundance of magnesium-25 and magnesium-26. All right, so it does say here that it's 79%, so that's good to start us off with. It says that 25 and 26 are approximately equal. So if we do a little bit of math here and take 100 minus 79, get that in my calculator, that's 21. I know that, but I'm still going to punch it in my calculator anyways. So we get 21% that's left over that's split between 25 and 26. So we're going to divide that by 2. So each of these should have 10.5% relative abundance. So if I draw this in the graph here, that's probably a little bit too big, but 10.5% right there. Erase a little bit of that first one. No, I'll just erase the whole thing. So again, 10.5%, perfect. Okay, so awesome. We're off to a really, really good start. It says, describe the difference in atomic structure that accounts for the difference in mass between magnesium-25 and magnesium-26. Well, they're both magnesium, so that indicates that they have the same number of protons. So we have 12 positively charged protons here and 12 positively protons here. So the difference in atomic structure that's going to account for the difference in mass is the number of neutrons, in which case magnesium-25 contains 13 neutrons, and in which magnesium-26 contains 14 neutrons. So that is going to account for the difference. So pretty easy mass spec graph to start us off. Let's see what we've got coming up next here. All right, so it says a student prepares a 1.85 times 10 to the negative third molar solution of MgNO3 in beaker 1 and a 2.80 times 10 to the negative fourth molar solution of NaOH in beaker 2 as shown. The particle diagram shown represents a magnesium ion in a beaker. A sodium ion in beaker 2 has a weaker attraction to water than Mg2+ does. Explain this phenomenon using Coulomb's law and each of the following. So we're going to use Coulomb's law to discuss the relative charge of the ions. Well, again, I'm not going to provide a full-length explanation written out for each of these, but we know that Mg has a 2+ charge, and Na has a 1+ charge. And so remember that the magnitude of charge is directly correlated to the strength of the attraction of the ion to the water molecules. So in this case, magnesium has a 2+ charge, and so therefore would have a stronger attraction due to the fact it is a 2+ charge when compared to sodium, which is only a 1+ charge. So that takes into account the relative charge of the ions that are present in the solution. How about the relative radii of the ions? Well, if we take a look at what's going on a molecular level, I'm going to go ahead and erase these here. We know that magnesium has 12 protons in its nucleus and sodium has 11 protons in its nucleus. And so this part of the question has to do with the relative nuclear charge. Both of these actually have the same number of electrons in their structure because they are both ions. So as a result, the strength of attraction to the water molecules is directly correlated to the number of positively charged protons in the nucleus or nuclear charge. So because sodium has a weaker nuclear charge, that is, it only has 11 protons in the nucleus when compared to magnesium, which has 12, this is going to have a weaker attraction to the water molecules, again, due to the fact that it has a smaller nuclear charge and has less attraction, of course, due to Coulomb's law, opposite charges attract. And the greater the magnitude of charge, the greater attraction, as well as the smaller the radius of the ion here. So this is going to have a much smaller radius due to the fact that the outermost electrons are going to be more attracted to the nucleus due to it having 12 protons. So this has a greater nuclear charge, and so as a result, its atomic radius is smaller. And we know that smaller ions tend to have greater attraction to water molecules through ion-dipole intermolecular forces. So takes care of that question. Let's take a look at the next one we got here. We have it's asked us to calculate the pH of the solution in beaker 2. So we have a 2.8 times 10 to the negative fourth molar NaOH solution. So 2.80 times 10 to the negative fourth. Again, that's a molar solution there. So because this is a strong base, I can take the negative log of this concentration so negative log of 2.80 times 10 to the negative fourth. That will actually give me the pOH of the solution. And remember, we can take 14 minus the pOH to get the pH of this solution. So we'll take the negative log of, so negative log 2.8 times 10 to the negative fourth. And what I get is a pOH that is 3.55. And again, if we subtract that from 14, we will get the pH of our solution. So 14 minus the 3.55 gives me a pH of 10.45. Okay, so there's the first couple of questions done. Let's see what we got up next. Nothing too difficult here. Nice little introduction. All right, so for part D here, it says a student combines 35.00 milliliters of a 1.85 times 10 to the negative third molar MgNO3 solution with 50 milliliters of 2.80 times 10 to the negative fourth NaOH, as shown in the diagram. It wants us to calculate the Mg after the two solutions are combined, but before any reaction takes place, and assume that the volumes are additive. So in order to actually go through and calculate the concentration of magnesium after the solution has been added, we need to know two pieces of information. We need to know the total number of moles of magnesium over the total volume of the solution. So if we're adding 50 milliliters of solution with 35 milliliters, we know our total volume is going to be 85.0 milliliters, or, because we're asked to calculate the concentration, 0.085 liters. In order to get the magnesium, we're going to have to get the magnesium out of this MgNO3 here. So in order to solve for the moles of magnesium, we are going to take our molarity here, 1.85 times 10 to the negative third, set that equal to our molarity. Remember, molarity is moles over liters, so 0.035 liters. And we'll solve for X here. Now, the moles of MgNO3 and moles of Mg are in a 1-to-1 mole ratio, so whatever we solve for on top of this molarity calculation is going to be the same as the number of moles of Mg in the solution. So we're going to take 0.035. We're going to multiply that by 1.85 times 10 to the negative third. And what we end up with is 6.48 times 10 to the negative fifth. And then we're just going to simply divide that out and get our new concentration of magnesium in the solution. So we're going to divide that, 6.48 times 10 to the negative fifth. And we're going to divide that by 0.085 liters to get our new concentration of Mg. And our new concentration of Mg is 7.62 times 10 to the negative fourth. And that is molarity of Mg2+. All right? So again, fairly straightforward there. Let's move on and see what we have for the next problem. Just scroll down here. All right, so it looks like we have a solubility equilibria question here. It says the dissolution of magnesium hydroxide is represented by the following equation, and you're given a KSP value. It says write the expression for KSP. So let's do that first. So part I here, KSP is equal to, remember, anytime we do equilibrium, it's products over reactants and coefficients become exponents. So it's going to be Mg2+ times OH minus, and then we are going to square that because of that coefficient there. It says, after the two solutions are combined in beaker 3 as described in part D, but before any reaction takes place, the OH minus is 1.65 times 10 to the negative fourth. Using your answer in part D, calculate the value of the reaction quotient. So in this case, we're not going to be solving for K. We're actually given the value for K, but we're going to be solving for Q. And it appears in the next question, we're going to be comparing Q and K in order to figure out if a precipitate is formed. So let's get some pieces of information here. Remember, we solve for Q the same way we solve for K. The only difference is that Q is when we're not at equilibrium yet, and then we can utilize that information in order to figure out what direction the reaction goes in order to reestablish chemical equilibrium. So we're going to go ahead and plug in our OH minus. Our Mg actually comes from part D. So I'm going to scroll back up to the top here. It's at 7.62 times 10 to the negative fourth. So we're going to plug that in here. So 7.62 times 10 to the negative fourth. And then what we're going to do is we're going to quantitatively go ahead and solve for Q. So let's plug that into our calculator. So we're going to take 1.65 times 10 to the negative fourth. We are going to square that. Then we're going to multiply that by 7.62 times 10 to the negative fourth. And I get a value that is 2.07. So 2.07 times 10 to the negative 11th. Okay, so there's our value for the reaction quotient Q. And then it says using Q and K, determine whether a precipitate forms. So the first thing we need to do is look at the values for Q and K and figure out which one is bigger. So when we compare Q and K, Q is bigger than K. And a couple ways to look at this. You can just memorize this, but what I like to do is I like to tell my students to go ahead and follow the mouth. If we follow the mouth, that means that the reaction is going to shift towards our reactants in order to achieve equilibrium, and we're shifting towards our solid. And so because Q is greater than K, the reaction is going to shift towards our reactants, which is where the solid is. And so as a result, the answer is yes, we are going to form a precipitate as a result of this. All right. The last question here says that in a separate experiment, the student adds HNO3 to decrease the pH of a saturated solution. Does the amount of undissolved MgOH2 increase, decrease, or remain the same? So if we think about this from an equilibrium standpoint, I'm going to go and get rid of this information up here. Adding in HNO3 is a strong acid, and so that contributes a lot of H3O plus to our solution. Well, what H3O plus does when it reacts with the OH minus here is it neutralizes it to produce water, and so as a result, that drops the OH minus concentration. When it drops the OH minus concentration, Q no longer equals K. The system then responds by shifting to the right in order to reestablish chemical equilibrium. And so as a result, more of the solid is going to become aqueous ions. So when I read the question again, it says, does the amount of undissolved MgOH2 increase, decrease, or remain the same? Well, the amount of undissolved is going to decrease because when we add in HNO3, it's a strong acid, generates H3O plus ions, it neutralizes the OH minus, decreasing the OH minus concentration. When that happens, Q no longer equals K, and the system responds by shifting right to reestablish equilibrium. Thus, more of the undissolved MgOH2 will become dissolved. So as a result, it will decrease. I think that might be it for question 1. Okay, question 1 in the books. It is done. We only have 6 more questions left, and we are finished. So let's go ahead and move to question 2. If you just saw question 1, that's all you want to see. Stop the video right here. Thanks for watching. We'll see you next time. Question 2, let's move on.